Hello everyone, and welcome to another edition of Everything You Wanted to Know About Storage, but Were Too Proud to Ask. If you're a veteran of the Too Proud to Ask series, welcome back. If this is your first time though, this is a series that explores some of the foundational elements of storage that you may run into in the course of any IT job. So there's no need to fake it till you make it, as we've got your back. So we try to clarify some of the terms that can easily be confusing if you don't understand the tribal knowledge surrounding storage. So today's presentation is just one of those topics too, and I just see there's a question about no audio. Can everybody hear me? I don't want to go too far without people actually being able to hear. All right, well, I'm going to continue just in case. So let's see, today's presentation is going to be one of those topics too. So today in part Aqua, we're going to be covering storage controllers, which, as you may have already experienced, can mean different things depending upon which part of the system you're working on. So today's webinar is packed with all kinds of superlative goodness. My name is Jay Metz, and I am truly fortunate to have significant industry powerhouses to make me look good. First, we have Craig Carlson, who is on the board of directors for SNIA, NVM Express, and the Fibre Channel Industry Association. We also have John Kim, who is the chair for SNIA's Ethernet Storage Forum, who sponsors these Too Proud to Ask webinars. Peter Onifric is also on the board of directors for NVM Express, as well as the chair of the NVMe Management Interface Working Group. And last but certainly not least, we have Chad Hintz, who is a principal systems engineer and a member of the Ethernet Storage Forum as well. So our sponsor for today's session is the Storage Networking Industry Association, and the SNIA has the support of and participation of thousands of industry professionals just like you. From standards to education and testing to compliance, SNIA is the go-to organization for all things storage. So one quick detour into the administrivia. We'd like to point out that while the material contained in this webinar is copyrighted by SNIA, any member organization or individual members may use the material as long as the slides are reproduced in their entirety without modification, and SNIA must be acknowledged as the source. To that end, let me address one of the questions that always comes up. As usual, these slides will be made available after the webinar is over at a link that we're going to provide at the end. Speaking of questions, we want to keep this presentation to under an hour, and we have a lot of material to cover. So if we don't get to your question live on the webinar, we will answer it in the blog afterwards, I promise. So let's begin and get to the meat of the matter. We're here to talk about storage controllers and all the various contexts that apply. But why storage controllers as a topic? Why does it deserve so much love? Well, one of the things that I've noticed is that the term controllers is highly contextual. That is, depending upon what you're focusing on, the meaning can change in really significant ways. When software people talk about controllers in a DevOps setting, for example, they mean something very different than when networking people talk about controllers, which is very different than when storage people talk about media controllers. What this means in real terms, then, is that when storage people use the phrase controllers, there are two things that are supposed to be intuitive. First, what exactly is being controlled, and of course what is not. And second, what is the scope of that control and what it actually means. Now, if you're extremely familiar with storage, it often becomes too easy to forget where those lines are drawn. In systems that have multiple controllers, it's easy to get really confused. So, to that end, what are the goals of the webinar? Now, way back at the very first webinar in the Too Proud to Ask series, part Chartreuse, we spent a little time talking about controllers and what they meant. That was just a taster, though. Here, we're going to be going a bit deeper into the subject so that you can have a better understanding of some of the important distinctions between different types of controllers. This includes, but certainly not limited to, media controllers, software controllers, direct attached storage controllers, and storage area network controllers, and so on. And you can start your drinking game anytime you want. So, the purpose here is not to get you to memorize each of the different specifics of each of the controller type. What we hope that you'll get out of this is that there is no one ubiquitous understanding of a controller, and in fact there might be some overlap. We want to point out those areas and how to avoid confusion. To that end, we're going to start off with a broad overview of what storage controllers actually refer to in a general sense. And from there, we're going to examine different types of controllers for both the direct attached storage devices as well as storage area network devices, before taking an almost criminally short look at management controllers for storage. And finally, last but not least, we're going to be changing gears radically and take a look at the logic controllers for both software-defined networks and for software-defined storage to show that quote-unquote software-defined doesn't necessarily mean the same thing for the respective control planes. Now, with that, let me shut up so that we can get to the good stuff. And Craig Carlson is going to kick things off with those foundations. Craig?
All right, thanks, Jay. So we're going to do a quick dip into a storage controller 101. And so the first question is, what is a storage controller? We kind of need to pull it back a bit and talk about what a controller is in computer systems in general. And general, a controller is either a logical physical entity that manages the data between two different entities. And so those can be two different entities either on the same system or separated by a network. In particular, a storage controller is a device that converts between the OS storage commands and the system bus or network to the storage device. Also, a storage controller could also reside on the storage device to manage the specific storage media. So a storage controller functions in general. So the OS will send a set of commands that it wants to send to the storage device, and this can include read, write, format, what have you. The storage device storage controller hardware or software converts this set of commands from the OS to the storage specific interface and protocol. The controller may also access host memory if needed for a specific command, such as a read or a write. And then the controller communicates with the storage device in its native protocol and interface. And of course, if there are any responses or data returned, the storage controller returns that to the host. And a little bit about how we are using controller here. Most of the time when you hear controller, we're probably talking about what we talk about is the front-end controller, which resides in the host. But there's also the controller that resides many times in the storage device as well. And that we're calling here the back-end controller. And this controller provides access to the specific storage media. This could be as simple as a very simple device all the way up to a large disk or all-flash array. And then for memory access, the storage controller on the front end, the host storage controller, typically accesses the host memory through what's called a scattered gather list. For data writes, the SGL or scattered gather list tells the controller which memory to read from, and for data reads from the storage device, the SGL tells the controller which memory to write to when the data is received. This data read and write process is performed typically by direct memory access to and from the controller card or device. And typically this direct memory access is performed independently of the host CPU so that the host CPU doesn't have to waste cycles moving data around. So that kind of leads into the next slide here, hardware offload. Also, beyond the DMA engine, many times controllers use hardware offload to process commands. And this offload is typically a hardware accelerated path for the routine command operations, such as read, writes, things like that. The non-routine events, such as error processing and other exceptions, is still typically done in software, but that's not typically a performance path. It's the performance path that's usually accelerated for hardware offload. And the advantages of this include lower latency for command processing, potential lower power usage, and also offloading the tasks from the host CPU. So the task of reading, writing, or accessing the storage device takes less CPU cycles than the host CPU. then controller processes the OS commands to the native storage protocol, and there are many of these out there. And some of these could include SCSI, NVMe, FICON, SATA, NFS, or others. So there's also typically a native interface that the storage device is running on. And this interface could be any one of Fibre channel, SAS, serial attached SCSI, Ethernet, SATA, and there are also many others out there. And so the key takeaways from this section are that the controller can mean different things depending on context, and that could be a front-end or back-end controller. Controllers are an interface between devices and manage either the commands from the OS or the physical media on the back end. And storage controllers may support one or more storage protocols. And with that, I'll send it over to John.
Thank you very much. Jay, any comments before I start on the SCSI controller section?
No, I think that you're good to go.
All right. Hello, everyone. So I'm going to cover SCSI controllers. So a SCSI controller is an adapter which manages connections to SCSI devices. So it sounds pretty straightforward enough. Typically, it's used to connect most often to hard drives or flash drives, but it can also be used to connect to scanners or other peripheral devices. Now, this adapter is usually, most commonly today, it's a serial attached SCSI or SAS host bus adapter, and it could be an add-in PCIe card in the computer, or it could be a chip built into the motherboard or a chip built into device. Now, a SCSI controller, as I was just getting ahead of myself for a second, is not only the adapter, but it could also be a controller that's in the SCSI device itself. So, for example, in the scanner or in the hard drive or in the optical drive. And this controller responds to the SCSI commands, and it talks with the adapter controller. So you typically have a conversation between a SCSI controller adapter and a SCSI controller in the device. You can also send these SCSI commands over a network. So network adapters, which we'll talk about like Fibre channel or Ethernet or others, USB, can carry SCSI commands, but they are not themselves SCSI controllers. So just a little example here, going back to Mark's example earlier. We have the host OS, which sends SCSI commands to a SCSI controller adapter, which is usually a card, but again, it could be a chip built into the motherboard. And then this converts those into the physical signals that go to the SCSI device. And it goes over a wire connection and goes to the SCSI device. In this case, it's a drive, but it again could be other devices. And then the SCSI controller on the device responds to those commands and typically sends data back, either writes data or reads data and then sends it back to the SCSI adapter controller, which then passes it back to the operating system and to the application. Now, what is the SCSI I'm talking about? So SCSI stands for Small Computer Systems Interface, and it's a standardized command set which is mostly oriented around reading and writing of data, but there are other control commands, so it's not only about reading and writing data. It doesn't have to be just about storage, though that is the most common use case. It's a standardized command set, but there are different ways you can transmit it physically. There are different physical connection options that will carry the SCSI commands. So, for example, way back in the early 80s, if you remember the 80s, we started with parallel SCSI, which had many physical connections in a wide ribbon cable. And then we had a Fibre channel, which could carry these SCSI commands. And then we had iSCSI. And around the same time iSCSI was invented, we had serial attached SCSI, or SAS. And that's the most common physical connection today, especially for local SCSI devices. But there are other methods. I won't go into the details here, but you have the SCSI RDMA protocol. You have the iSCSI extensions for RDMA. You have a SCSI over USB. So you could connect, you'll use a USB cable and send SCSI signals over that USB cable as well. And this diagram here shows some of the common networked SCSI options. Basically, the two most common ways are to run SCSI commands over the Fibre channel protocol and over a Fibre channel connection, or FCOE. And then you can also run iSCSI over TCP networks, which run over the IP protocol and run over physical Ethernet. So those are probably the two most common ways of running SCSI commands over a network. And this diagram just shows, as an illustration of how you could have local SCSI access versus networked SCSI access. So on the left, we have the operating system sending SCSI commands. So it sends it to the local SCSI host bus adapter, or HBA, and that then translates the signals off to whatever the hard drives or SSDs are speaking, and it sends the data back and forth. So that's a local SCSI access. But the operating system could also send those SCSI commands to a fiber channel or Ethernet host bus adapter, or NIC, and that adapter will then carry those SCSI commands over the network to another similar network or fabric adapter in the storage controller or storage target. And then from there, the SCSI commands are then sent to again, a SCSI controller in that storage box, which then talks to the SCSI devices. The one interesting observation is that's not the only way you can do SCSI over the network. You actually could send SCSI commands over the network and then have the storage controller in its software work its magic and convert those and talk to other storage devices that are not SCSI. So on the right-hand side, where I have all these devices that say hard drive, HDD or SSD, hard drives or solid-state drives, those could be SAS or SCSI devices, but they don't have to be. They could be NVMe, they could be SATA, they could be other types of storage devices, and a storage controller can translate SCSI commands into those devices. So the key is that when you have local SCSI, it pretty much goes to a SCSI device. But when you send it over a network, it's a SCSI protocol and SCSI commands, but they could be translated into non-SCSI storage devices by the magic of the storage controller. And finally, a couple examples of actual SCSI controllers. Again, they can be a PCIe card or a chip built into the motherboard. And then some of them just do SAS, but a lot of them can just speak SAS or SATA. Some of them actually also have built-in RAID controllers. Some of them support NVMe. And a SAS expander allows you to connect more SCSI devices to one connector. Normally, a SAS connector supports 4 devices. With a SCSI expander, you can have many more. And here we have some pictures of actual SCSI controller devices from different vendors. Right, so key takeaways, SCSI controller means the SCSI adapter. It can send SCSI commands over different connections, including a local SAS connection, but also different network connections. Local SCSI or direct attached storage, DAS, uses local SCSI devices, and network SCSI might or might not use SCSI devices, but it transmits the SCSI commands over a network. All right, Jay, that's the end of my section. I return it back over to you or on to Craig.
Well, let's go ahead and give it to Craig. There are some questions that are there for Craig, but will probably make more sense once he finishes his section.
All right, thanks, John and Jay. So we're going to take a quick look at fiber channel storage controllers. So the task of fiber channel controller is, first of all, to provide discovery of devices attached to fiber channel fabric, which is a network of devices, and this is performed through accessing the fiber channel name server. It also provides access to the fiber channel management server, which allows for zoning configuration and other management tasks. The fiber channel controller also typically provides a hardware offload. Many of the fiber channel controllers do that, and also provides interface to the physical transport, which right now is a 64 GFC, which stands for 64 gigabit fiber channel. Fiber channel protocol stack. In a typical fiber channel protocol stack, there are multiple protocols supported, and that includes SCSI, FICON, NVMe, and also TCP/IP, which in this case is not necessarily a storage protocol, but it is part of the stack. In this figure, the controller portion is where the line is with controller, which is the FCP line for the storage protocols, and IP over FC for TCP/IP. FCP is used by many of the fiber channel storage protocols as the transport engine, which transports the commands and data across the wire. One new storage protocol has just been added to the list. The set of protocols that are available on fiber channel is NVMe or Fabrics. This is the most recently supported storage protocol, which has been defined by the FC NVMe project within T11, and this was first completed end of 2016. T11 is now working on the FC NVMe2 project, NVMe2 project, which is the main goal of this one is to find enhanced error recovery, and that's to support the higher speeds that are coming up in the future. Of course, there are also some protocols that have been on there for a long time on Fibre Channel. SCSI has been supported on Fibre Channel since 1994, and FICON has been supported on Fibre Channel since 1996. So the Fibre Channel controller tasks, the controller receives a SCSI, FICON, or NVMe command from the OS. The Fibre Channel portion of the controller does a lookup on the name server to find out where the storage device resides on the fabric. And once that lookup is performed, then it sends a Fibre Channel frame with the command to the specific device. FC frames are sent on a native Fibre Channel or an FCOE link. And the backend controller receives the Fibre Channel frames and forwards the specific commands to the storage devices for processing. And so the takeaways from these slides, from this section, Fibre Channel has supported SCSI and FICON since the mid-90s. NVMe over FC is the newest addition. And in a typical Fibre Channel system, multiple storage protocols can be supported at the same time on a single port. And with that, I'll turn it over to Peter.
Thanks, Craig. Okay, so a controller in the context of NVMe could mean one of three things. It could mean an NVMe controller. An NVMe controller is the logical interface between a host and NVM subsystem. It could mean an NVMe-MI management controller. A management controller is a logical entity that manages one or more NVMe storage devices. Or it could mean an NVMe SSD controller. An NVMe SSD controller is a physical component used to implement an NVMe SSD. Let's take a look at these in more detail. This slide shows an NVMe controller, which is a logical interface between a host and an NVM subsystem. The reason it's a logical interface is because the NVMe controller and NVM subsystem are architectural elements in the NVMe architecture, and there are many possible implementations. You can think of an NVM subsystem as a PCIe SSD. In this example, the NVM subsystem contains one controller and a non-volatile storage medium, which is exposed to the host as two namespaces, A and B. A namespace is a collection of logical blocks and is similar to a LUN in other storage protocols. The host communicates to the controller through submission-completion queue pairs. The host submits a command to the controller by enqueuing it on a submission queue. The controller processes the command, and when processing is completed, posts a completion back to the host on a completion queue. Associated with an NVMe controller, there is one admin queue pair and one or more I/O queue pairs. When PCI Express is the NVMe transport, then the NVMe controller is a PCI function. In other words, there's a one-to-one correspondence between PCI functions and NVMe controllers. When PCI Express single root I/O virtualization or SR-IOV is used, this can be an SR-IOV physical function or virtual function. This slide shows a dual-ported NVMe storage device, which could represent a dual-ported 2.5-inch SSD. In this case, the NVM subsystem contains two controllers, one for each host. The controllers are completely independent and each have their own queues and process commands independently. The controllers can provide access to private namespaces, such as A and C in this example, or namespaces that are shared and accessible by both hosts, such as namespace B in this example. This slide shows an NVMe storage device that supports PCI Express I/O virtualization, or SR-IOV. SR-IOV allows a guest operating system running in a virtual machine to have direct access to virtual functions. When used with NVMe, each virtual function is an NVMe controller, and the guest OS runs a standard NVMe driver. The hypervisor has access to a physical function that is also an NVMe controller and is used by the hypervisor to access storage and to manage the virtual functions. So now that we know a bit about NVMe controllers, let's take a look at NVMe in general. The NVMe is made up of 3 specifications. The NVMe base specification, or just NVMe, defines the NVMe architecture, the NVMe command set, and how NVMe works over PCI Express. The NVMe over Fabric specification, or NVMe OS, extends the NVMe architecture and command set to general interconnection networks. Finally, the NVMe management interface specification, or NVMe-MI, defines the architecture and command set used for out-of-band management of NVMe storage devices. Let's take a look at out-of-band management in more detail. Out-of-band management is management that operates with hardware resources and components that are independent of operating system control. The entity that performs this out-of-band management is called a management controller. A management controller is sometimes referred to as a baseboard management controller, or BMC, and has management responsibilities such as determining what NVMe SSDs are plugged in, configuring these SSDs, and monitoring their health. This slide shows the NVMe management interface protocol layering. At the bottom, we have the NVMe storage device that represents an SSD. Out-of-band management is supported over 2 physical interfaces, SMBus I2C and PCI Express vendor-defined messages. On top of the physical transport, there's the Management Component Transport Protocol, or MCTP, that provides reliable transport of messages. And on top of the transport, we have the NVMe management interface itself, which defines the out-of-band management architecture and command set. On top of NVMe-MI, we have the management controller, which is the entity that performs this management using NVMe-MI. And on top of that, we may have management applications. This slide shows an M.2 NVMe SSD. The SSD contains NAND flash, DRAM, and an NVMe SSD controller. An NVMe SSD controller is the physical component used to implement an NVMe SSD. Thus, the NVMe SSD controller in this example is used to implement an NVM subsystem and NVMe controllers, which are the logical elements in the NVMe architecture introduced earlier. This slide shows the internal of an NVMe SSD controller. It contains a PCI Express interface. Next to that, we have a queuing interface that implements the NVMe admin and IO queue pairs. Next to this, we have command processing logic that processes NVMe commands and issues appropriate flash operations. These flash operations are sent to a flash interface that interfaces the NVMe SSD controller to external NAND flash. Since NAND flash is error-prone and can introduce errors, the NVMe SSD controller contains an error-correcting block and uses an error-correcting code, or ECC, to fix errors. Finally, the SSD controller may contain a DRAM interface to external DRAM. This DRAM is used to hold mapping tables necessary to implement the SSD. In summary, a controller in NVMe can mean one of 3 things. It could mean an NVMe controller, which is the logical interface between a host and an NVM subsystem. It could mean a management controller, which is used to manage NVMe SSDs. Or it could mean an NVMe SSD controller, which is a physical device used to implement an NVMe SSD. Together, these 3 types of controllers allows one to build a storage system using NVMe. And with that, I will turn it over to Chad to talk about SDN controllers.
Thanks, Peter. So thanks everyone for having me. And you're probably wondering, why is a networking guy on here talking about SDN controllers when we're talking about storage controllers? So what I'm going to go through with you is what is storage networking, or a software-defined networking and software-defined storage controllers, and what's the difference between them. As you know, storage runs on a network, so we have to make sure that we understand what type of networks are being implemented nowadays and understand the background, but also to what Jay said early on. Controllers mean different based on who you're talking to, and you've already seen that through most of the presentation today. So we're going to get into that from a networking standpoint, but we'll also compare it to what a software-defined storage controller is, and not all software-defined means the same. So with that said, let's just get into it. So what is SDN? Well, it matters who you ask. There's a lot of different variations of it, and based on who you talk to, just like we've talked about from a storage controller perspective, it could mean different things to different people. So we'll go over the major ones that we see from an industry perspective, but let's get into some basic definitions. So an SDN controller originally when it was created, it was made for separating the control plane from the data plane within networking devices and making it easier to manage your infrastructure. From that SDN controller, we would use open-based protocols and push that information down to switches and routers to be able to send packets, basically create the flows of the network. So let's get into what that actually means. This is what a traditional network looks like. This is just one diagram of the network. But you'll notice that in this diagram of the network that every single networking device, whether it be a router or a switch, each one of them has what we call a control plane and a data plane, right? Control plane is where we learn what we need to do from a forwarding perspective, and the data plane is where we put it into action or where we actually forward packets. So as networks started to grow, what we wanted to do was try to figure out an easier way to manage, because every single networking device, if it has its own control plane and its own data plane, in the traditional way of doing networking, each one of those pieces of hardware were also a piece of management. So as networks grew, we added a whole bunch of pieces of management from an operational perspective that could be cumbersome to a lot of customers, so and IT network administrators. So SDN came out originally, and in its first iteration was, okay, well, the easiest way to do that was let's centralize all the management of that, and let's centralize the decision-making process, which is the control plane, into a controller. So the original implementation of SDN, or the original thought process of SDN, software-defined networking, was that we were going to centralize the control plane. So what happens is, as they all move to the controller, the control plane all goes to that controller, and each one of the routers or switches in the network are really just left with a data plane to be able to forward packets. All the information built about what they're supposed to do from a forwarding perspective, or the decision on the forwarding, is all centralized in that control plane and then gets pushed down to them. But just like we learned in wireless many years ago when we centralized wireless and we centralized to what we call a controller-based wireless, in a lot of ways we needed a way to put information out at the edge. So out at those networking devices, there were some reasons why we wanted to have the control plane and data plane local for local decision-making process. But we needed to figure out a way that we could centralize the management of it, but still keep the control plane and data plane in the networking devices. So SDN has evolved, and that's why, based on who you ask, you might hear about multiple different ways of doing SDN, or software-defined networking. As we talked about originally, the first iteration is that you have a control plane and data plane is residing in each box. The second iteration was the centralizing of the control plane, like we just talked about, and using standard-based protocols like OpenFlow to be able to send down information about the flow information, or how we're going to make our forwarding decision. And then let each router and switch with the data plane make that decision, or start forwarding on it. The hybrid one is more of a way of, we keep the control plane and data plane in each one of the devices, but we also have a centralized control plane that might do it based on intent. It might do it based on there's cognitive ways. There's also a way of doing it where you're just doing the traditional, I'm learning from a control plane like you did inside the devices, or you did in the purest SDN way, and then you push it down to the local control plane, and they can make decisions as well. So in a hybrid SDN world, what we've seen is that because we need intelligence at the edge, like we talked about, we start to see an evolution where people are centralizing the management and northbound API or access into the network, into those controllers, or interactions with those through orchestration and automation tools. But each one of the devices has its own control plane and data plane. So from that perspective, any device can make its own decisions. It will get intelligence from the centralized controller, but it will also be able to make local decisions, which are usually faster. But it also gives you the ability that if the intent or the control plane controller is to go down, that I can still use the last known good state of the network, or whatever's been pushed down to me to say this is what I want, or the steady state. I might not be able to create new flows, or might be able to not be able to create new intent because my centralized control plane is down for the SDN controller, but I could still run the network. So what does this have to do with software-defined storage? Do they tie together? Does a software-defined storage controller mean the same thing as a software-defined networking controller? Let's get into that. Well, first of all, some of the similarities that they have is they both abstract the underlying hardware and management control plane perspective. So the software-defined storage controller, his job is to provide visibility and provisioning to the underlying infrastructure, but abstracting that from the view of what's above it. So from an orchestration or whatnot, or from a management control plane perspective. So you go into the software-defined storage controller, you're able to provision what you need. It will then take care of all of the provisioning below without having you to have to go to each one of the underlying controllers in each one of the boxes. Well, software-defined networking does that as well if we centralize, as we talked about. But in the grand schemes of things of how they interact, they really don't have anything to do with each other. Really, the SDN controller, the only thing it can do, or the software-defined storage controller, is that they will allow northbound API access to an orchestration or automation tool, so they can interact that way, but tied together, they're really not. They're really separate from each other. So that answers the question, does software-defined storage controller or software-defined networking controller, are they the same thing? No, they're not. So what is an SDS controller? As I mentioned earlier, really its job is to sit in between the orchestration tools and your SAN, your storage subsystems, and be able to provision what is needed to be done below in the underlying hardware while abstracting that to the upper layer orchestration or applications. So as we've talked about already through this, where does SDS and SDN really interact then? Well, really, they don't have interactions with each other directly, but if I have a software-defined storage implementation and controller, that's going to talk to northbound to an orchestration or automation tool through the northbound APIs. And the same thing happens with your software-defined networking controller. So the software-defined networking controller is going to open northbound APIs that's going to be able to talk to the orchestration or automation tools, and that's where they will be tied together. Not directly between each other, but mostly through an orchestration or automation tool. So the key takeaways of this is that they are not the same. That SDN is primarily used to manage the flow and creation of networking devices. And SDS controllers are paid for the visibility and provisioning of the storage resources that are below them. Do they abstract the underlying information or hardware that's below them? In a lot of ways, yes. Do they provide the same northbound API to tie into applications and orchestrations? Absolutely. But they are totally different, even though they're both starting with software-defined. So with that, I'll pass it over to Jay from a summary perspective.
Great, thanks, Chad. As we're approaching the end of the webcast, let's tackle some of the questions that have come up during the course of the webinar. So the first one actually goes to Craig. You had mentioned direct memory access, and there's a question that came in based on what you had said. How does DMA result in lower power consumption?
Yeah, that's a good question. So the way that DMA can result in lower power consumption is that it offloads a task from the CPU. And generally when you offload a task from the CPU, you are lowering the power consumption because, you know, if you look at a system that might have a Xeon processor on there, that CPU takes a lot of power. And any cycles you waste or not waste or use whatever moving data means that you have potentially higher power usage within that CPU.
Groovy. And following along that, it looks like you're gonna get a few questions, and I do recommend that if anybody has any questions right now, they can feel free to shoot them over to us at the moment. So in regards to and this actually can go to either you or Peter. what does the term fabrics mean in the storage context? And I know it gets a little bit further out of the scope of this, but I think it's still relevant for us to talk about. So what does the term fabrics mean in a storage context?
I'll take that first, and Peter can follow up with from his perspective. In general, fabrics means it's a very generic term for the network in a storage, a network-attached storage. And what that network consists of depends on the specific technology you're using. For example, in a fiber channel fabric, the fabric consists of one or more switches which are interconnected to provide that network access.
Okay.
Yeah.
Peter, did you want to add something?
Sure. So, we have the NVMe over Fabric specification. So Fabrics is used in that title. And really the intent was when we first did NVMe, it was for direct attached PCIe SSDs. And what we wanted to do was to extend the NVMe architecture over general interconnects. So by Fabrics, we mean, things like Fibre channel, InfiniBand, Ethernet, or even on Ethernet, the various protocols that are on Ethernet. So it's really a general way of stating general interconnects.
Cool. And this one does fall outside the scope of this particular presentation, but we've got a little bit of time, so we can go ahead and address it here. What are the length limits on NVMe over Fibre? And I think they mean Fibre channel here. Greg, do you want to tackle that one?
Sure. There really isn't a length on NVMe over Fibre channel. The data transfer can be as long as it needs to be. Multiple frames can be put together to make any length of a transfer. And I think the question might come from, if you look at the Fibre channel frame, the length of the Fibre channel frame is about 2K, a little bit more. But that's very similar to most other network protocols. They all have a certain frame or packet length, and you can string multiple frames or packets together to make a larger data transfer.
Okay. And we have another question that just came in. Does storage controller bridge the gap between low-performing host bus operations versus the high-speed system bus operations? That's an excellent question. Who wants to tackle? John, you want to take that one?
Sure. So the low-performing host bus operation, so typically the system bus is running at a higher speed and, direct memory access, and then the host bus adapters, the host bus operations, are at a lower speed, first because they're going through the PCIe bus, which may provide some limit on the performance, and second because the connection from the host bus adapter out either to the physical devices, the storage devices, or across the network might be slower. It might be only 16, 32, 10, 25, or 100 gigabits a second, and the connection to the storage devices might be lower. For example, SAS might be 12 gigabits a second maximum. So it certainly bridges the performance. The storage controllers certainly are translating requests that come from the system bus out to the host bus side. And they do that. And sometimes they will use caching or other techniques to accelerate that. So for example, if you request data frequently, the same data, the storage controller might cache it on an NVDIMM or in DRAM or on some other type of storage like 3D crosspoint or something, and so that you can access it more quickly, more closer to system bus speeds than on the host bus speeds. But generally speaking, yes, the requests that come in on the system bus have to then be translated to the host bus side by the storage controller. And the other way you can speed up access is by going to multiple storage or multiple host bus adapters. So requests on the system bus or coming at the CPU and memory speed could then be spread across multiple host bus adapters or network cards or storage controller cards, depending how you want to do it, so that even though each one of them cannot keep up with the system bus speed, you can spread the requests across many of them to get faster performance.
Great. So, it looks like, oh, I'm sorry, it looks like I probably overspoke somebody. Somebody else want to add something? I thought I heard something.
No, I'm done with that one.
Well, I think that, you know, one of the things that we've managed to succeed in doing is getting the imagination flowing for people, because the questions are sort of building upon what we've talked about, and in a very nice way. We're gonna address some of the questions that fall a little bit too far outside the scope of this particular presentation in the blog, where we can point you to some additional information. But at the end of the day, there are a couple things to keep in mind. First, depending on your background, the term controller can be confusing. And so our goal was to try to help clarify some of the meanings behind the term and where they fit into the typical data center. So we hope that that's been successful in that. Now, obviously, it was impossible to go through all the possible storage controllers, let alone in detail. But we did want to emphasize controllers at the direct attached level, the storage area network level, as well as the software level. And we know that any one of these topics deserve to be examined in far greater depth, but that's okay. For now, we wanted to be able to touch upon the first step in removing some of the confusion, and it sounds like from the questions we've been able to build upon those. We will be able to build upon those quite easily. As it is, this is our 9th Too Proud to Ask webcast, and we want to thank you, the viewers, for making it such a great success. This means that there are 8 more webinars that go back to the basics and help you get over that awkward social anxiety when your storage friends start rambling on. This includes everything from block, file, and object I/O all the way to storage management and several points in between. Now, having said that, we're going to be putting that knowledge to good use when we take it to the next level at our Great Storage Debate series, this one pertaining to different storage networking protocols. So make sure to mark your calendars for June 21st. And finally, please, please, please rate this webcast and provide us with feedback. We always want to know what we did right and what we might have missed. Your input is extremely important to us. And for those of you who asked questions at the last second, we will be getting to them in our Q&A blog. So, you know, even though we're getting closer to the end, we'll still be able to answer those questions for you. Finally, you may want to consider following us on Twitter to find out more information and announcements of webinars like this one, as well as other events. So, last but not least, I want to give you a big heartfelt and truly sincere thank you from all of us here at SNIA, and on behalf of the presenters. Thank you for attending this webinar, and we look forward to seeing you again. And again, please don't forget to leave a rating and feedback. Thank you so much, and thank you to the presenters for all the time you spent preparing this material.